Okay, for today, you're going to realize we skipped 10.2. Basically, it's only the vocabulary I want you to pull out of there. But for 10.3, we get back into some theorems that we need to know to basically be able to utilize. Not really much else. So if you look in your note packet on page 290 and 291, you're going to find that there are 4 theorems that are very important to the lesson. The first one is theorem 10.6, which is congruent corresponding chord theorem. Sorry about that. And what that's basically saying is this. I have a circle, and if they are congruent distance, so this is C and this is B, this is A and this is D. So if they are the same length here, then the arch in which they are attached to or to the outer part is also going to be the same distance. So that's basically what it's talking about. It says in the same circle or in congruent circles, 2 minor arcs are congruent if and only if their corresponding chords are congruent. And remember, we talked about this earlier. This right here is considered a chord. So let's look at 10.7, and this is perpendicular chord bisector. Remember, with a perpendicular chord bisector, it sounds just like it is. You have to have the diameter. So here's my diameter, and here's E. And let's say I have a chord that cuts through here, and this is F, G, and D. If this is a true perpendicular bisector, then we know it makes a 90-degree angle. So we know if that is true, then the diameter is cut, then EG is perpendicular to DF. Remember, EG is your diameter and EF is the chord. So if that is true, then HD, line segment HD, is going to be congruent to HF. And that means that the arches then, our arch, GD arch, is then congruent to our GF arch. So if we say that these two are congruent here, then once again, these two are congruent there. All right, and then theorem 8, the perpendicular chord bisector converse. The converse is stating the opposite. If I am told that one of the chords of a circle is perpendicular bisector of another chord, then the first chord is the diameter. So let's say I have my circle here, and this is cut here, and this is cut here, and this right here is a right angle. And I tell you that these two are perpendicular to each other, these two lines, and that this is a 90-degree angle causing it, and that the distance between T and P is the same distance between P and R, then that means that SQ has to be the diameter. That is, like I said, it's a converse, so basically it's working backwards. So if you were given this and told specific things, we could then make the justification that SQ is the diameter. And then the last theorem is equidistance chord theorem, and that is 10.9. And in 10.9, what it says, in the same circle or in congruent circles, 2 chords are congruent if and only if they are equidistant from the center. Now, equidistance has to be signified somewhere. So let's make 2 chords here. And if I have this here and this here, and these right here are both right angles, let's call that E. This is going to be G, and this is going to be F. That is A, C, D, and B. All right. So if this is true, that means that AB is congruent to CD. So in other words, the lengths, they are equidistant from each other there. If and only if those two, if we say they are the same length, then we have to prove, then if that's the case, then this here and this here are the same. So if they are the same, then we can conclusively say that EF is congruent to EG because of this first statement. And once again, remember, they have to make 90-degree angles. If they're not making 90-degree angles, then they are not a bisector, which means then the equidistance is not going to work here. All right, so now that we have the theorems under our belt, let's actually take and move into what the work's going to look at. So that was 290 and 291. Let's go on to 292 in your note packet. In 292, basically, we have this lovely little drawing here. And we have a rectangle set within, and mine's not very perfect, but hey, it works for the time being. So this is X and W. Q is my center. I have Y and Z. So this right here is 9.2 for the length. This is 42 degrees for the center here. And then the length up here is 3.6. So what I'm asking for here is, for the first one, what is the measure of the angle WQX? All right, so if I'm looking for that, or the arc of that, we are looking at the fact that if we know that this is here, we can say that this is a vertical angle, which means that that's going to be 42 degrees because it is vertical from ZQY. So we know that's going to be 42 degrees. Number 2, it asks, what is YZ? Well, YZ is the length here. Well, we just proved that this here was 42 degrees also. So if this is 42 and this is 42, then the lengths on each end are going to be the same. Also, the arches are the same, but for right now, we know that this is going to measure 3.6. Okay, so we can say if vertical angles, then YZ is 3.6. Okay, number 3, it wants to know WZ. Well, this one goes off vertical angles also, but it's going to be a little different than you think. I'm going to grab a different pen here. So we know this right here is 42. So 42, if I take 180 minus 42, this here is going to give me 136. I'm sorry, 138. So in a sense, we're doing number 4 before we do number 3. Because if we can prove that these two angles are the same, which they are, then the lengths on each side is also the same. So we can prove by subtraction. So for number 4, we can say 180 minus 42 is 138 degrees. So we're going to say over here by vertical angles, WZ is the same length as XY, which is 9.2. So that's just one way to do that, but it's easier to prove it by the angles, because we had already stated that if the angles are the same, and in this case, then it's going to make it easier. Okay, so that is 1 through 4. Let's look at number 5. So for number 5, we have a circle here, and it looks like we have a perpendicular bisector. So I have a right angle over here. Here is Q, P, R. The middle here is T. My radius marker center of the circle is O, and S is on the far end. Now over here it tells me this is 2x minus 4.1, and down below this is it's x minus 0.5. Well, we know that if they are truly a perpendicular bisector, then these two are the same. So you're just going to set them equal to each other and solve. So I'm going to subtract x across, and it'll give me x. I'm going to add 4.1 across. When we do that, we're going to get 3.6. So x is 3.6. That's all it asked for, by the way. It didn't ask for what the measurement was. It just wanted to know what x was. So look at number 6. Same thing here. A little different, but the same idea. G, I, right angle. This here is H. The center of the circle is W, J, and K. This here is going to be 3x minus 5, and below it's going to be 2x plus 1. And it's once again the same thing. If these two are perpendicular bisectors, and it goes to prove that these in JH and HG have to be the same. So we're just going to set them equal to each other. 3x minus 5 equals 2x plus 1. We subtract the 2x across, which gives me x. Add the 5 across, and it gives me 6. So 6 is my x. Okay, in number 7 here, we're asked to find the radius, right? So number 7 takes a little more work, 7 and 8. It says find the radius of the circle. So the first thing we're going to do is, of course, I'm going to draw it out. There's one chord here and one chord here. We have that there, and then this here. Sorry, it's not perfect. This right here is a 90-degree angle, and this over here is a 90-degree angle. It says this is 3 and that is 3. So the lengths of these are the same length, so therefore that gives us our proof that we need for this. So the first thing we're going to do with this is, if that's true, then our chords are the same, okay? So we know that we can work backwards. We know that in this case, BP and PE are the same length. So therefore, I know that the chords are the same length. And the chords is 5x minus 2, and then this chord over here is going to end up being 3x plus 2. And let's label our chords so that we have a reference point as we talk about this. Okay, so the first one we're going to do is solve for x. So we're going to set them equal to each other. So solve for x, and when we do that, we're going to get 5x minus 2 equals 3x plus 2. So that gives me 2x, and this over here gives me 4, so x equals 2. Step 2 in this is going to be plug it back in. So plug back into x. So when I do that, I'm going to end up with 5. This becomes a 2 in here, minus 2, so 10 minus 2 is 8. Now, this basically makes a right triangle. So if you think about it, it looks kind of like a right triangle here. So if this full length here is 8, now we know that, then we only need half of it because this cuts it in half. So half of this is going to be 4. So let's do Pythagorean theorem. So step 3 is actually do Pythagorean theorem. Whoops. Pythagorean theorem. There we go. So we're going to do, we know this length here is 3, and this here now is 4. So 3 plus 4, each one of them squared, equals c squared. And c squared, if you notice, is the radius, because it is from the center point to the outer edge. So that hypotenuse in this triangle is going to create my radius. That's why we're doing the Pythagorean theorem. So I have 9 plus 16 equals c squared. So I'm going to have 25 equals c squared, or 5 equals c. So 5 is the answer for the radius. So radius equals 5. Now, number 8 is the same way. The only difference is here is that we're looking for the inside. So if we look for that, we have these two chords here. and from here to here. Now, once again, these are right angles. This time, though, instead of knowing not knowing what the chords are, we know that they are 20. So each chord is 20 this time. This length here is what we don't know. And we were told that if we know the lengths are the same, then these two here, if they make right angles, are going to be the same also. So this right here is 4x minus 5, and this guy here is x plus 4. So first thing we're going to do is solve for x. So let's set them equal to each other. Subtract that across, so I get 3x. I add 5 across, get 9, so x equals 3. So right there's step 1. Step 2, I'm going to plug it back in. So I have 4 times 3 minus 5. So I'm looking at 12 minus 5, which is 7. So now we have part 2. So part 3 is the Pythagorean Theorem. And remember that we're going to make it here, because this length from the center point to the outer edge is what creates the radius. So let's think about this logically. We know one of the legs now is 7, and we know that the other one is half this chord. So half of that chord is going to be 10. And then c squared is going to be the radii. So this is going to be 49 plus 100 equals c squared. So this is 149 equals c squared. Now, before I would tell you you need to leave it as a radical. And in this case, we do not need to. So we're going to turn it into decimal. So it's actually 12.2 equals our x, or our radius. And that is the end of 10.3 video.